So the aim of today's lecture is just to give you an overview of the subject and also briefly tell you what kind of things we will learn as we go along in this course. Okay. So let's if I kind of look at the origin of this subject. So some of the initial questions which were being asked, which led to development of this field, was to understand what controls the flow of heat. Better now. So some of the initial questions were what controls flow of heat, and again when I'm saying flow of heat from one object to another. Okay, to understand the relationship between heat and work. So work here, for example, refers to the mechanical work. Okay, so when I'm saying the relationship, the questions being asked were, can I convert heat to work? Vice versa, can work be converted to heat? But more important was converting heat to work. And it makes sense also, right? By converting heat to work, for example, you can move a machine, you can move a steam engine, so on and so forth. Okay. And if I can convert heat to work, then how much of the heat can be converted to work? So can I convert? If yes, then what percent of heat can actually be converted to work? Can I convert all of heat to work? You will see answer under most circumstances would be no. Okay. So those are the things you would learn. Right now it looks a little abstract, but you will see this course is quite generic. But once we start talking in terms of specific problems, then of course it becomes very definitive. Okay. So that transition you would see several times. In terms of the meaning of the word thermodynamics, does anyone know what's the meaning or how what is the kind of origin name of these words? So it is coming from thermos, which in Greek means heat, and dynamics you're already aware. Okay, so dynamics of heat. That's how the word is coming. If I look in terms of modern day usage, so what I told you was some of the very traditional questions being asked. Okay, if I look at current usage of the subject, it's much more diverse. So we are talking about multi-phase, multi-component systems, solution thermodynamics, and pretty much all of material science. Again, in terms of specific examples, as we go along, we'll discuss. But if I take a look, the subject is quite generic in the sense that pretty much each department at IIT Delhi would have a course in thermodynamics, either a core course or elective course. Okay, mechanical engineering, chemistry, physics, our department, of course, even humanities, we don't have here, but there's a branch of thermodynamics known as sociological thermodynamics, which is taught in humanities departments. Okay, in some of the universities. So we'll see as again, even in this lecture, we'll see why the subject is so generic. Okay. So for this lecture, the objectives are simple. We'll just learn what is the relevance of the subject to chemical engineers. We'll take a look at some of the properties, definition of properties, and we'll see lot of thermodynamics is run in terms of these properties. Many times our only aim is what I call as property calculation, calculating a value for a given property. That is one big input from thermodynamics. Okay, and some initial laws of thermodynamics. We'll discuss just two: zeroth and the first law of thermodynamics, if the time permits in this lecture. Otherwise, it might spill over a little bit to the next lecture. In terms of just kind of recalling or at least doing the basic homework, go through your physical chemistry notes. I hope in one of the chemistry courses you must have gone through few things about thermodynamics. If not, that's okay. But if yes, then please review those notes. And most of this lecture and the next would be based on chapter 1 and chapter 2 of the textbook. Okay. The textbook would be Smith Van Ness, 6th edition. The reason I'm mentioning 6th edition here, there is not a lot of difference between various editions, is that the problems, some of the problems that I'm giving you from the book, the problem numbers would be based on 6th edition. But along with problem numbers, I also supply a brief statement. So looking at the brief statement, even if you have a different edition, you would be able to identify the correct problem. Okay, but please keep in mind the problem numbers would be correct only if you are looking at the 6th edition. For other editions, look at the brief problem statement to identify the problem. Okay, so back to this point on origin of thermodynamics. Okay, so the key question, as I mentioned, was converting heat to work. Specifically, at that time, the question was, can I convert the chemical energy stored in fossil fuel, for example, coal, in into work? Okay, so the chemical energy was being converted to heat first, for example, to maybe make steam, and that steam was somehow being converted to work to move a steam engine. Okay, so then first question was, how much energy is stored in coal or steam? So that is in some sense a property question. So this is addressed by what we call as the first law of thermodynamics. Then the second question was, earlier I stated how much heat can I convert to work. So that in some sense boils down to how efficiently can the energy be converted from one form to another. So that means we'll see both heat and work are also being taken as forms of energy in the subject. Okay. And the question we are asking is, how efficiently can I convert one to other? You will see this question would be answered by entropy and the second law of thermodynamics. And the third related question is, can you convert at all? So is that process possible? Feasibility. That also is answered by second law. Okay, so is it possible? How efficiently you can do it? And lastly, I'm interested in actual values, absolute values. How much energy I have in the first place? So those questions would together allow me to understand, for example, how far the steam engine can move per kg of coal. Okay, so that is a basic question. If I have 1 kg of coal, how far my steam engine can go? These three answers together would give me that one answer or one number, which is the distance per kg of fuel. Okay, any questions so far?
No,
Okay,
sir.
so let me give you, so you will see that even though the subject doesn't have, so all these three laws of thermodynamics, the first law, the second law, you will also see the third law, they are actually empirical in the sense that no first principle proof exists for them, and therefore, but again, no counter has been found to them also. Okay, so what is more very important in thermodynamics is precise definitions, because you don't have maths at the base. So therefore precise definitions become very important. Okay, so for example, have you heard of the statement that entropy cannot increase, or sorry, entropy cannot decrease, or entropy always increases?
Yes, sir.
Yes, sir.
Okay, but just that is not correct. Just saying entropy always increases or entropy always decreases without further qualifying this statement is incorrect. Okay, similarly saying I cannot convert all of heat into work is incorrect without further refining the statement. Okay, so therefore definitions statements in thermodynamics are precise, and they are precise for a reason, because any deviation from that precise statement would mean that it is not in general true, and therefore it cannot be called as a law. So let us look at the first definition of thermodynamics. So I'm still not coming to the laws, just coming to the definition of the subject. Okay. So so of course this need not be precise. This is just telling you what we mean by thermodynamics. So you can note it down if you want. Thermodynamics is a science, and more importantly, an engineering tool used to describe processes that involve change in system properties. So I will repeat up to this point. Thermodynamics is a science, and more importantly, an engineering tool used to describe processes that involve change in system properties. So what could be system properties? For example, temperature, pressure, composition. Okay, so we are defining a process which involves changes in these properties. Other aspects of the process could be transformation of energy, and the relationship between heat and work. Okay, so I will say it together now. Thermodynamics is a science, and more importantly, an engineering tool used to describe processes that involve change in system properties, transformation of energy, and the relationships between heat and work. So all the keywords which were relevant I have put here. And as I mentioned, some of the features of the two, or at least two key features of the subject, which already mentioned, but I will again reiterate. One which I mentioned was it is extremely generic. So all departments at IIT Delhi, other places, would have a subject on thermodynamics. Okay. And again, the reason it is so generic is because we are not making any hypothesis concerning the structure and type of material. So there is no initial hypothesis or restriction concerning structure and type of material. So it is applicable to collection of people, collection of stars, collection of atoms, so on and so forth. Okay. So you can see the wide scales we are looking at. If it's a collection of stars, I can in principle apply thermodynamics. Collection of people, sociological thermodynamics, I can apply thermodynamics. Collection of atoms, materials, I can apply thermodynamics. Okay, so there is no initial hypothesis. That is why it is so generic. Okay, and the other underlying principle, which I've already mentioned again, is no first principles proof. So in that sense, the starting point of the subject is not mathematical. However, those precise definitions you will see as we go along can be converted to exact maths. So once you have given a definition, that definition can be converted to a very precise mathematical equation. So once you believe that definition, then the subject is entirely mathematical, very logical. Okay, so just the initial entry point is in a way saying that please believe me. But beyond that point, the subject is extremely logical, extremely mathematical. Okay? So in fact, a lot of progress in thermodynamics has happened because of mathematics and vice versa. A lot of new things in mathematics have come from thermodynamics or development of thermodynamics. Okay, why do we need thermodynamics? Okay, so it addresses questions of efficiency and feasibility that we have seen, of converting chemical energy into useful work. Okay, so you can see that even the initial questions were dealing with conversion of chemical energy into something useful. So it's directly therefore relevant to us as chemical engineers because we deal with these questions all the time. Okay, any process, any operation I want to carry out in a plant, I will need to design a reactor. In a reactor, you are at times converting one species to another, so you're carrying out a chemical reaction. So and I want this reactor to do the job as efficiently as possible. Okay, so as again through this course as well as maybe chemical reaction engineering course, you would see you have many options, many conditions at which you can run your reactor, many temperatures, many possible pressures. What is the best temperature? What is the best pressure? What additional things you need? For example, catalyst. Sometimes you require catalyst, sometimes you do not. All those questions are answered by thermodynamics as well as the subject of chemical reaction engineering. Okay, so therefore it is very important for us as chemical engineers. So let us take a look at some examples now. Okay, on the same question. So I'm taking one specific example of a refinery. In a refinery, two kinds of broad processes are happening. One I'm calling as physical transformation, where basically you are saying crude is a mixture of many small and long carbon chains. And in physical transformation via distillation process, I am separating those fractions. So I'm separating fractions of crude on the basis of differences in their volatility, and that I am accomplishing via this distillation process. The reason we are calling it as physical transformation is because no bond formation, no bond breaking is happening. You're only separating components like water and oil. Okay, if you have a water oil mixture, if you leave it for some time, oil will start to float over water, and then you can somehow scoop away oil, and you have affected a physical transformation. Okay, the other process which is happening in refineries is, for example, making polymers, nylon. So there you are taking these smaller starting units, carrying out, for example, polymerization reactions, radical based reactions, so that what you get is petrochemicals. Nylon is one example. Here, bond breaking, bond formation is happening, and therefore we are calling this as a chemical transformation. Okay, so both physical and chemical transformation will require some input of energy. So that is one question which will be addressed by our subject. Second question is the process that I have designed, is it feasible at all? So again, the question would be addressed by thermodynamics. What is the efficiency of my process? For example, if I'm talking about distillation process, then I can ask for per rupee how much energy I am inputting. And the rupee is coming because I'm selling these products. I'm selling gasoline, I'm selling diesel. So that gives me money. Okay. So how much energy I am adding to the process, how much steam I am using, so that I'm getting this physical separation. And is my process cost viable? If my process cost is not viable, I need to change the conditions at which I am operating to make my process viable. Okay. So crude cost is what it is. So I cannot change the crude oil cost much. So whatever crude oil cost I'm getting from international market, I'm getting, but I can optimize my process. I can reduce the operating cost. Okay. So part of that answer will come from our subject thermodynamics. how to optimize, how to work at the best possible conditions so that you can get the end result. End result is physical transformation. Okay. So these I have already stated. We will address questions pertaining to feasibility and efficiency. We will estimate material properties. So that's where the second very important thing of thermodynamics comes. Whenever I'm designing a reactor, I need to know at what conditions I want to operate, and at those conditions, what are the material properties. Okay, so given a particular temperature and pressure, what is the specific heat capacity of crude oil? The specific heat capacity of crude oil will tell me how much energy is required to take it from one temperature to another temperature. So specific heat capacity is a material property, which in turn might be dependent on conditions I am working at. So pressure and temperature are the conditions I am working at. And the target is take the crude oil from T1 to T2. The answer is heat required is integral of CPDT, right? The heat required for that process would be this integral. Cp is the material property that I want to know so that I can design my process. Okay. So property estimation would help me in designing a process. And lastly, you will see you need very good understanding of phase and reaction equilibria that I've not discussed as much right now. But you can see in physical transformation, you are dealing with phase equilibria. You have two phases in a distillation tower, liquid and vapor. So you need to understand phase equilibria. If you're carrying out chemical transformations, you have a mixture of reacting species and you need to deal with reaction equilibria. So phase and reaction equilibria are very two or very important concepts which for any process will have a great relevance. Okay. Now something which we will not cover in this course but is also very important is thermodynamics at nanoscale. Okay, so when I say thermodynamics at nanoscale, that means we are dealing with entities which are very small in size. For example, protein molecule, which is a few nanometers in size. So even at that size scale, you will see thermodynamics plays a very important role. So in this cartoon picture, I'm showing you a protein molecule, which can either, so protein is a polymer of amino acids. Okay, so this protein molecule can either exist in an open structure, which we call as unfolded, or it can be existing in this more compact conformation, which we call as folded. So again, in some sense, you can visualize this as phase equilibria that have two possible phases of a polymer protein chain, either open or closed. This particular folded state is very relevant from functional perspective. So here I'm showing you in the bottom part an enzyme, and the way this enzyme functions is that the protein molecule, so enzyme is a protein, okay, it takes a specific shape. You can see in the first part of that picture, it is taking a specific shape so that the reactants which are in green can come and bind to the protein, and they're binding because of chemical as well as shape complementarity. So these two sub chemicals bind to my enzyme because the enzyme has taken this specific shape, and all of this is happening automatically in a way. Okay, so the nature has given the correct set of amino acid to this protein. So we call that as the amino acid sequence. So which amino acids in which place is sufficient to determine what shape this protein molecule will take. Okay, and once it takes a particular shape, particular conformation, it can perform its function. So function here is these two species must come and bind to the protein. Once they bind, they are in close proximity now, so they can undergo a reaction. So they undergo a reaction and form products. Once the products are formed, the shape of the products is somewhat different, or on the formation of products, the shape of the protein changes somewhat. Either way, once the products are formed, they are able to move away from the enzyme. Either the shape of the product is somewhat different or the shape of protein has changed. The end result is a reaction has happened catalyzed by the enzyme, and in this case enzyme is a protein which has taken this particular shape because of its chemistry. Okay, so broadly I have mentioned why it is happening. So there are two contributions to energetics here. So all questions of protein folding can in general be simplified to just a balance of two terms, enthalpy and entropy. Together, enthalpy and entropy give you what we call as free energy. In this case, I'm showing gives free energy. So enthalpy and entropy together gives free energy. All of these three which I have listed here are again thermodynamic properties. So if I can calculate enthalpy, I can calculate entropy at given conditions. I will be able to calculate the free energy, and that calculation of free energy will tell me which state the protein molecule will exist in, unfolded or folded. Okay. On the right, I'm showing you example of a different process using the same concept of hydrophobic interactions. And the reason I'm calling it dynamic assembly would be clear soon. Okay. So here I'm showing you an ant raft, so to say. Okay. So what is happening here is when there is some flooding, thousands of ants will come together and hold hands, so to say. And the belly of these ants is somewhat hydrophobic. So once all of these ants come together, they are able to entrap an air pocket, and that air pocket allows them to float. Okay, so it's a at the end a very simple explanation. And the reason I'm calling it as dynamic assembly is because ants are spending some energy in holding hands together. So only if they hold hands together, they will be able to entrap a large enough air pocket. Individually, they will not be able to do so. So they have to stick together so that they can entrap this air pocket and float. Okay. So this ant raft picture, of course, was published here, but it also appeared in one of the magazines which we have subscribed for our 6-year-old highlights. Okay. So it doesn't stop at publications. Sometimes you will see these things will come to much wider audience also. All right. So that is why we're calling it as dynamic assembly. So overall, this word here, assembly, is very important in thermodynamics, especially when we are dealing with thermodynamics at nanoscale. Okay, by tuning chemistry, you can tune enthalpy entropy balance, and by tuning enthalpy entropy balance, you can take your system to functional states. Those functional states we call as self-assembled states. Okay, and if in addition you are using some external field, for example, in this case it is the work of ants, then we call that as a dynamically assembled state. So self-assembled if no external field is being used, dynamic assembly if external field is being used. The end result is same. You are going to a functional state to perform a specific function. For the enzyme, it was to perform a reaction. For the ant raft, it was to be able to float so that they do not submerge in flood water. One more example of kind of same thing. So here again, thermodynamics at nanoscale. Again, the idea is to perform a function. In this case, the function is controlled drug release. So I'm not going to go into details, but again, the chemistry has been tuned so that the system has colloids as well as polymers. So the system can take different conformations, different morphologies, can have different rheological properties as a function of temperature. So your switch here is temperature. As you change temperature, the system can go from very liquid like to gel like. Okay, and now you can see that given a drug molecule, it will have very different diffusion transport properties in one state versus another. Okay, so by changing temperature, you can switch on, switch off drug release. So that similarly, by changing pH, you can switch on, switch off drug release, so on and so forth. Okay, so in both cases, the idea was to tune thermodynamics, enthalpy, entropy balance by tuning chemistry and external parameters like temperature and pressure, so that you can get the end result, which is very dependent on the structure. So therefore, we call these as structure property function relationship. Okay, so structure will give you some particular property. That particular property will be desired to perform a particular function. Any questions, queries so far?
No, sir.
No, sir.
All right. So now we'll become a somewhat more specific. Okay. So up to this point, the discussion was more generic, just to give you an overview of where the subject might be used, what we mean by thermodynamics. So now we are going to add some more specific details in this lecture. Okay. So let us first look at thermodynamic properties. Okay. So again, because of its widespread use, there are various ways by which you can do classification of thermodynamic properties. Okay. So we are going to take two particular routes. So for thermodynamic system or overall thermodynamic process classification, so one classification will do at the system level, and again this will be clear as I discuss that, and the other classification will be attempting at the property level. So I'm starting at property. You can have the so-called intensive properties. Example I've given here: pressure, temperature, chemical potential. And the reason we call them intensive is because they are independent of the quantity of material. Okay, so that is the keyword here. These are independent of quantity of material. If you have a glass of water, when you're defining its temperature, you say its temperature is 25 degrees Celsius. Okay. Now, if you add more water, add same temperature to this glass, you have 2 kg of water, but temperature is still 25 degrees Celsius. Okay. So temperature is not dependent on how much of that substance you have. Similarly for pressure and chemical potential. So therefore, these are intensive properties. Whereas properties that are dependent on the quantity of material. So same example, instead of 1 kg, now you have 2 kg of water. Okay. So that is we call as extensive property, because now the property is dependent on the quantity of material. So the examples which I've given here is volume, internal energy U, enthalpy H, entropy S, Gibbs energy G, and on each of these I have put in superscript a T. So in general, that means we are defining our property, extensive property, as MT, where M could be any of these V, U, H, S, or G, and it will be dependent on the quantity of material. Quantity of material here is N. Okay. Extensive property has even more specific meaning. So I'm saying it is dependent on the quantity of material, but in thermodynamics, this has a very precise relationship. Okay. So let us see what is that relationship. So if I have lambda into n moles of something, and the value of that property, whatever property I'm interested in, let's say enthalpy is mt, this would be equal to lambda times the value of that property for size n, or you can further say lambda into n times the value of that property for size 1, that is for 1 mole. This has a special name. We call this last quantity, which is the property of 1 mole or 1 kg, as either a specific or molar property. If I'm defining the value per mole, I will call it molar property. If I'm defining the value per unit mass, I will call it as specific property. Okay. So number one, an extensive property is dependent on the quantity of material. Number two, that dependence is very precise, given by the formula given here. Okay. So it's a linear function. So MT is a linear function of specific or molar property. Okay. And that is a third category I've defined here, molar and specific properties. So here I have added some more symbols. Xi's are your mole fractions. Wi's will use for mass fractions. Rho for density. V specific volume. U specific or molar internal energy. Similarly, H, S, and G would be specific or molar enthalpy, entropy, or Gibbs energy. These are also, you can see, intensive. The reason these are intensive is because you are fixing the quantity of material. And that is different from saying that independent. So I have mentioned intensive properties at the top: pressure, temperature, and chemical potential. They are truly independent of quantity of material because I'm not defining there 1 mole, 1 kg, etc. All right. Whereas molar and specific properties are also independent, or also intensive properties, but they are intensive because I am predefining the quantity of material as 1 kg or 1 mole. So is that difference clear? In the intensive properties at the top versus the molar and specific properties at the bottom, why they have been separated?
Yes, sir.
Okay. So the intensive properties do not have any extensive counterpart. Pressure, temperature, chemical potential, there is nothing like PT or TT or mu T. Okay. Pressure, temperature, chemical potential have no extensive counterpart, whereas your molar and specific properties, which are defined at the bottom, do have an extensive counterpart. That is why I put them separately. All right. One more way by which you can do property classification is by defining something as state versus path dependent. So let us see what it means. So let's say this is my system in state A. Right now, you don't even know the meaning of thermodynamic state. That definition will come later. But let us say that has a very fixed meaning. So let's say state A represents some thermodynamic state for a given material, and state B represents another thermodynamic state for that same material. There might be various possible ways, which I'm calling as paths, by which I can go from state A to state B. So I'm going from one state to another state via different paths. If the property of state B versus state A. So let's say in thermodynamics, you will only talk about property change. So let's say the Gibbs energy change in going from A to B. I'm calling this as a state variable or a state property. The reason is Gibbs energy change in going from A to B is not dependent on the path. Whereas heat and work requirement. Okay, so that's where you will see even the questions of efficiency will come. So Q and W are not state properties, they are path dependent properties. So you can see here, in some of them, the requirement of heat or work might be smaller than other. So which path to take can sometimes be governed by thermodynamics after taking other considerations also. Sometimes we will see that the thermodynamic path which is most optimal is not practical, in a sense that it is going to take me 1 year to go from state A to state B. I cannot wait 1 year. So I might have to change my conditions somewhat so that I take a less optimal path, but I'm able to finish my process in 1 hour rather than 1 year. So therefore, just thermodynamics will not be sufficient. Kinetics is also important, and the marriage of two will give you the most optimal answer from time as well as money perspective. All right. Anyways, here each path can in principle have different Q and W, heat and work. So such properties which depend on the path, we call them as path properties. Properties that do not depend on the path, we call them as state properties. Okay. So pressure, temperature, volume, internal energy, enthalpy, entropy, Gibbs energy. You don't have to remember them. Okay. Once you understand the subject as we go along, you would know intuitively which is a path property, which is not. Okay. Now let us come to our next classification, which was on the system side. Okay. So I have to define any thermodynamic process. I need two things. I need material. I need to define system. So to classify material, we have already talked about two different ways, either in terms of intensive versus extensive, or in terms of state versus path dependent. Okay, so those are defining my material. Also, to an extent, process. The second thing which I need to define my process is I need to define my system. So when we are defining our system, automatically I have to define my surroundings also. So this definitions would be clear only if you realize that it is system and surroundings together that in a way form the thermodynamic universe. So whatever is outside the system is surroundings. So system I define very precisely, and then I say whatever is not part of my system is surroundings. So therefore, system plus surroundings together gives you the thermodynamic universe. Okay, and now the system and surroundings can talk only via two things. One we are calling as energy, second we are calling as mass. Okay. So, and then I define my system on the basis of how the system and surroundings are talking to each other. Okay. So if the interaction is such that mass exchange is not happening, but energy exchange is happening with the surroundings. Okay. So here red line I'm denoting for mass. If it's solid, that means it is opaque to that line. So opaque to mass in this case, transparent to energy. So energy exchange is allowed, mass exchange is not allowed. Such a system we call as closed system. Okay. So for now, let us just go through this definition. Why this is so important would be clear in maybe 2 or 3 slides. Next possibility is transparent to both. Transparent to mass, transparent to energy. Such a system we call as an open system. Okay. Last, opaque to mass as well as energy. So this system we call as an isolated system. Okay, so three kinds of system depending on interaction of energy and mass. Fourth possibility is also there. Transparent to mass, opaque to energy. I have not discussed that. Any ideas why?
Moving mass will carry energy.
Yes. So mass itself contains energy. So exchange of mass automatically means exchange of energy. Therefore, this last possibility is not feasible. You cannot have a situation where mass is being exchanged, but energy is not being exchanged. At least not in general. Okay, you might be able to devise a very specific scenario where the mass exchange and energy exchange can cancel each other out. Or sorry, the mass exchange and other means of energy exchange cancel each other out so that you have no energy exchange. But that is a very specific scenario. That is not a general scenario. Therefore, we don't have to define it separately. Okay. So correct answer is mass exchange itself means energy exchange because mass carries energy with it. Okay. So why I am so concerned about the type of system? Remember earlier I asked you half precise statements, are those correct or not? For example, entropy will always increase or entropy will always decrease, or I cannot convert all of heat to work. So all of those answers can only be made precise if you define the system, if you define the process precisely. So that is why this definition of system is important. Okay. So it is very important to be careful about the type of system you are considering. The rules, that means the thermodynamic laws. And when I'm saying the laws will not change themselves, but the mathematical form of the law will change. Okay, so when I'm saying the thermodynamics rules that apply change in very subtle ways, the change is in the mathematical form. The first law of thermodynamics is not dependent on system. The second law of thermodynamics, the definition is not dependent on system, so on and so forth. However, the mathematical form of the first law is dependent on the system. There is a different equation for open system, there's a different equation for closed system. Okay. Similarly, when you come to second law, the mathematical form of the second law in terms of entropy would have a different form depending on the type of system. Okay, so therefore the rules will change in very subtle ways depending on the details. Okay, details could be constant pressure, adiabatic, constant volume, so on and so forth. Okay, so depending on those details, your maths will change. So therefore, you have to be very careful about the details of the system, the details of the process. Okay, this last question which I put here, this will be part of tutorial or discussion. Okay, so heat capacity you would see is again either a path dependent or a state property depending on how you are defining it. It can be a state property, it can be a path property depending on how you are defining it. Second related question which I will take up during discussion session or during tutorial, whichever comes first, doesn't matter, would be the relationship between heat capacity, temperature, and heat exchange. Okay. So what we mean by heat exchange, what we mean by temperature, what we mean by heat capacity, how these three quantities are related to each other. That's another question which I will take up in discussion. And again, the reason I'm saying I will take up in discussion is that I want you to first think about those before you come to the discussion session. Okay. So first think about those yourself, and then we'll take them up for further refining. Okay. So now some of the thermodynamic variables which we are going to use a lot, I'm going to talk about them. The first one is temperature. So zeroth law of thermodynamics essentially provides us a definition of temperature. Okay, I will read it verbatim. If two objects are in thermal equilibrium with a specified object, then the two objects would be in thermal equilibrium with each other. And in fact, they have the same temperature. So in very small words, we are using temperature to quantify at least one part of equilibrium, which we call as thermal equilibrium. So temperature is a quantity which decides whether the objects are at thermal equilibrium or not. Okay. So this next picture will tell you that. So this is the zeroth law in kind of picture form. Okay. So object one here is my, let's say, thermometer. Object two and object three are my objects of interest in blue. If they are in thermal contact with each other, and I bring this third object, which is thermometer, in contact with these two, all three would have the same temperature. So of course I'm using this thermometer thermocouple to measure the temperature, and temperature of the thermocouple would be the temperature of object 2 would be the temperature of object 3. Okay, so that is the necessary and sufficient condition for thermal equilibrium. All right, there is another definition of temperature at molecular level. Can anyone tell? Maybe in your chemistry course you learned that relationship. If you take a glass of water, are the atoms or molecules at rest or they are moving? The glass of water is at rest. Okay, it is sitting on a table. But if you were able to look at individual molecules, what will you see? They will be stationary or they will be moving around.
Moving.
So moving.
Moving.
Okay, which we call as Brownian motion. But the center of mass is not moving, right? It is stationary. The center of mass is not moving, but individually each molecule is moving. So that motion or that energy which causes that movement, we call that as internal kinetic energy. The reason I'm calling it as internal is because the center of mass is at rest. So this is intrinsic to the constituent atoms or molecules that are forming up that material. They are constantly in motion, even when the center of mass is not moving, even when the system or the object is at rest. At the molecular level, there is a precise relationship. That means there is a mathematical formula linking the temperature to the internal kinetic energy. Have you seen that mathematical formula? You must have. Okay, so maybe go back to your physical chemistry notes, find out what equation you had which linked the two quantities, temperature to the internal kinetic energy. Okay, so that is at the molecular level. If I visualize my system, that is the definition I will give. Okay, so this I've already asked you for the discussion session. Think about this: how temperature, heat capacity, and heat, these three quantities are related to each other. Okay, units to measure temperature: Kelvin is the SI unit. Some other possible units are centigrade, Fahrenheit, Rankine scale. Next property of interest is pressure. So in terms, or let me just stop at this point for now. We'll continue in a minute. Any questions, any queries so far?
No, sir.
Okay. So pressure is force per unit area, and here we are defining the area as perpendicular to the surface. Okay, so let's say n represents the normal to any given surface. So when I'm defining pressure, I'm defining the force projected along n. So projection, so force is a vector. Projection of that force vector along this normal direction gives me a scalar. And if I scale that quantity or normalize that quantity by area, I will get pressure. Okay, so pressure is a scalar quantity. Force is a vector quantity. And the way we relate the two is by saying that it is the force per unit perpendicular area. That means projection of force along direction n. Units Newton per meter square. Some other units which we'll use: atmosphere, bar, torr, psi. Okay. And on psi, I can either define a gauge pressure, which I will note as psi-G, or absolute pressure, which I will define as psi-A. Okay. Do you understand the meaning of gauge pressure?
Yes.
So pressure I can write down as gauge pressure plus atmospheric pressure. So gauge pressure is the pressure above atmospheric pressure. And if you are in vacuum, then gauge pressure can be negative. That means the pressure can be less than the atmospheric pressure. Okay. So gauge pressure is absolute pressure minus the atmospheric pressure. And the reason I'm interested in gauge pressure many times is because that is what controls, for example, leakage. Okay. If the pressure goes below atmospheric, the chances of outside air leaking inside your system becomes very high. So once we go to, let's say, refrigeration, which is roughly sometime in the middle of the course, you will see this is a very important criteria. The gauge pressure in the refrigeration system in all places must be positive. That means the pressure must be above atmospheric pressure. Otherwise, outside air can leak into a refrigerator and, in a way, act as impurity for your refrigerant. Okay? So it will stop to work in the intended fashion. This is a device which is used to calibrate pressure gauges. So if you go to, for example, UG laboratory, you will see these pressure gauges which we are routinely using to measure pressure. But how do I know if this is accurate or not? So this dead weight tester is a device which is used to calibrate, to, in a way, certify a pressure gauge. Again, this is something which I will take up in either the tutorial or discussion session. And again, I want you to first go through this, see if you understand how it is working, and then, of course, I will provide my inputs. Okay. So, but main aim of this dead weight tester is to calibrate a pressure gauge. Because of its size, I cannot use it routinely inside laboratories. Okay, I cannot put dead weight testers on my reactors. I can only put a pressure gauge. So I'll calibrate my pressure gauge on a dead weight tester and then use that calibrated gauge to places where I want to measure pressure in a process. Okay. Next comes energy. So you can define, I mean, in terms of units, we use joules, or some other units which you use are BTU or feet pound force. Okay. So this particular system of units, this is essentially based on giving a single unit to force, pound force. And then all the other units are simply defined as kind of combined units. So for example, energy is force into distance. So work is force into distance. So therefore, one possible unit of energy becomes feet, which is the length unit, into lbf, pound force, which is the force unit. Okay. So in this system, the base unit is taken as pound force, lbf, and everything else revolves around that. Okay. Anyways, most of the time we'll be dealing with SI units, but I will want you to have some understanding of how to convert from one unit to another. Okay. So some understanding would be useful. Okay. Now on to types of energy. So I'm going to define two types: stored energies or transient energies. Remember, I said even work and heat will think of as forms of energy, but we are differentiating them to an extent. Okay. So I have three possible types of stored energies. In fact, what you will see is this internal energy is essentially, sorry, my bad. So internal energy itself, you will see, is composed of internal potential energy and internal kinetic energy. Okay. And this word internal, I already defined when discussing the internal kinetic energy, that this is the motion intrinsic to the material stored in the molecules. It is not dependent on macroscopic position or motion of your system or your material. Okay, so let's say I have a block. Let's say some material, block of wood. Okay, it might be moving at 1 meters per second, or it might be stationary. That means at rest. Okay, this block might be put on some height h, or this block might be at ground level. If I'm not changing the state of the block, let's say the state of this block of wood depends on three things: pressure, temperature, and composition. That is what is it is made up of. So if in these four situations, either the block is moving or stationary, either it is at height h or at ground level. If I'm not changing pressure, temperature, and composition, and let's say in general, if I'm not changing the thermodynamic state of this block of wood, its internal energy will not change. Okay, so internal energy is not dependent on the position or the motion of the material, and therefore we call it as internal energy. And besides internal energy, you can see in this situation, depending on the height, you can have potential energy for your system, so that we call as configurational or positional. Depending on the motion, that means motion of the center of mass, whether the block was at rest or whether the block was moving at 1 meters per second, it can have a kinetic energy. Okay, so you can have, because of the macroscopic position or motion, potential energy and kinetic energy components, and on top of that you can have internal energy, which itself is composed of internal potential energy, internal kinetic energy, and that we could just call as internal energy. So is the difference clear between internal energy and these other two, potential and kinetic energies? Okay, they are because of explicit motion, explicit position. And lastly, the transient energies, work and heat. The reason we call them transient is because these are relevant only for the duration of the process, or these can be defined only for the duration of the process, not before, not after. Okay, so I will come to this transient energies again in a while to make you understand more that why this work and heat are being called as transient energies. Okay, but as far as the stored energy is concerned, I hope that point is clear. Okay, so units we have already discussed, types I have discussed, internal energy, and the other two contributions, the potential and kinetic, we together call them as mechanical energies. That means you have two kinds of stored energies, internal and mechanical. Okay, kinetic energy I've already defined, energy stored because of motion. Okay, I've given a visualization. It can be thought of as rising from net work done on an object. So what here I'm trying to do is trying to link heat and work to other forms of energy. So let us see how this visualization can be made. So let's say same block of wood was initially at rest. So the velocity is 0 at t equal to 0. I start pulling it with some constant force F. After time t, it would have moved to a new position and its velocity will not be 0 now. Okay, it is moving with some velocity, and let's say I continue to apply that force F. So it will keep moving as a function of time. Okay, so what I have done here is in going from position 1 to position 2, I have done work on the system. In this case, the system is block of wood. And as a result of doing work on the system, I have obtained a finite value of one of the formed stored energies. In this case, that stored energy is the kinetic energy. So I've converted work in this case to kinetic energy. Okay. So that is first reason why I am treating work as a form of energy. Okay. Similarly, potential energy you can visualize. As I mentioned, this is because of position or configuration. Configuration I'm writing because if you visualize a spring, in a spring, depending on whether it is stretched or compressed, it can have an energy, and that energy we call as elastic potential energy. And because of position, the energy which we call as potential energy, that is the gravitational potential energy. And you can take the same example of the block of wood now. It is lying, let's say, at ground level. And you have a mechanism by which it can now be lifted to some height h. The velocity, let's say, is 0 in both places. So you can see now in this case, all the work which you did on this object has been converted to a stored form of energy, in this case, gravitational potential energy. This is an example of conversion of work into potential energy. Okay, we have 1 minute left. So this I showed you in terms of work. Now let us say I take water at 1 atmosphere and 25 degrees Celsius. And now I add heat to the system. Okay, you have put this beaker of water onto a gas stove. Okay, in doing so, let us say there is no appreciable loss of mass. Maybe you did it in a closed system and allowed the system to come back to 1 atmosphere. Let us not worry about those details. But during this process, you have taken the temperature from 25 degrees Celsius to 50 degrees Celsius. The beaker is lying where it was lying earlier. The beaker is not moving, but you have added heat. So you have added heat to the system. What did it get converted to? So in the earlier examples you have seen, work got converted to either the kinetic energy or the potential energy. In this case, you have added heat to this beaker. It is getting converted to something which, what is that? Is the question clear? Kinetic energy and potential energy have not changed. but something has changed. So what has changed?
Internal energy.
Internal energy.
Internal energy. So in this case, what has happened is when you heated this beaker, you have raised the internal energy. Okay. So we will make this connection more quantifiable. Okay. Via first law of thermodynamics. So far, what you have seen is heat and work are being converted to other forms of transient energy. I called heat and work as transient, other forms as stored energies. These connections, these reasons will become more clear once I give you the mathematical form of the first law of thermodynamics. So that's where we'll be stopping today for the Thursday. So let's assume this week's tutorial would be basically the Thursday lecture. So the Thursday session would be run as a tutorial, or you can say discussion session. Main thing which I'll want to do there is discuss design projects, discuss in more detail how the course would be structured, how the tutorials would be held. Okay. So those details we'll finalize, we'll discuss, and we'll solve some of the simple problems from practice set one. Okay. So I will share practice problem set one with you and solve a couple of simple problems in the Thursday session. Okay. So no tutorial per se this week, but the Thursday morning lecture session would be run as a discussion plus tutorial session. There any questions or queries? We have a minute I can take. Otherwise, you can wait till the Thursday session. All right. So we'll